work with relations. Students in a physics class are determining the resistance in a circuit by measuring voltage and current. So what's happening here is if you're putting half an amp of current through the circuit, that requires 6 volts. If you turn it up to 1.5 amps, that would require 18 volts. If you're driving 4 amps of current through this circuit, you would need a power supply that could give you 48 volts. At first they just say graph that data, represent the data on the grid. So they were putting a certain amount of current in first. That's your independent variable. And then as a result, they were seeing how much voltage. Let's see if I can write that sideways. Seeing how much voltage that was requiring. The current went up to 4 amps. And I've got 5 squares to work with, so I'm going to just say that's 1, 2, 3, 4 amps. That last square is a little bit wasted, which is too bad, but we'll live with it. And for voltage, we're going up to 48 volts. So 1, 2, 3, 4. If I make each of these 10 volts, 20 volts, 30, 40 volts, and 50 volts, that axis is just big enough. So half an amp of current would be right in the middle here. I don't have a line to guide me, which is unfortunate, but we'll be all right. And for voltage, if this is 10 volts, then this must be 2, 4, 6, 8, 10. Each of these squares is 2 volts, so 2, 4, 6 is my first point. 1.5 amps, again right in the middle, is 18 volts, so 10, 12, 14, 16, 18. 3 amps requires 10, 20, 30, 32, 34, 36 amps. 3.5 amps requires 10, 20, 30, 40, 42 volts. And 4 amps right on the line requires 10, 20, 30, 40, 48 would be right there. So, represent the data on the grid, done. Does it make sense to join the points together? Could we make a line? Would it be reasonable to make a line which goes like this? You might remember in the last example it did not, because we were talking about a number of triangles. And it turned out that if you have 1.2 triangles or 1.9 triangles, that doesn't make a great deal of sense. We decided that only whole numbers work properly in that situation. But current is measured in amperes, and you can have 1.5 amperes or 0.36 amperes, and that's no problem at all. And voltage measured in volts, you can also have 1.7 volts or any fractional number there, and that's no problem at all. So yes, in this situation, it is fine to have a straight line connecting the points. This is called a continuous relation, meaning it isn't a problem having fractions. If you're counting triangles or children or things like that, then fractions may not make sense, but for this one, yes, it's fine, because fractions are reasonable when you're measuring current and voltage. Use the graph to determine the voltage required for a current of 2.5 amps. They didn't mention that in our original experiment, but now that we have a line, the line can tell us things. 2.5 amps would be right here. From there, if you read up to the line, up, until you hit the line, and then you read straight across, this way, 30 volts it looks like. The line tells us, even though you didn't measure that point, assuming this is a straight line relation, pushing 2.5 amps through the circuit should require 30 volts. Write an equation expressing V in terms of I. Let's get back up to our data and have a look here. V in terms of I means if I give you a current, could you do some kind of number crunch and tell me what the voltage would have to be without having to look it up? Some of these numbers are decimals and are not terribly helpful here, so let's get those out of the way. these are nicer. From these, can you see the relationship? Think of it as, I give you 3, what can you do to it to end up with 36? And similarly, if I give you 4, what can you do with it to end up with 48? It seems like you take the current and you multiply it by 12. Looks like we have something where the voltage is the current multiplied by 12. How do you see that? Well, if you're not sure what to do with one of these, a good way to start is just take each of these numbers and divide it by its corresponding x, or its corresponding independent variable. So if you've got here 36 divided by 3, that comes out to 12. Try it again over here, 48 divided by 4, 12 again. If you start getting a consistent answer when you do this, that means you're onto something. It means this number 12 is something built into your equation. There's always a 12 relationship between those numbers. You remember over here we had 6 volts, 0.5 amps. 6 divided by 0.5 makes 12 as well. So it takes some trial and error sometimes, and some staring at it, and some talking to other people sometimes to figure out how these are going to work, but you're looking for some relationship that consistently ties together your independent and your dependent variables. For this one, looks like it's the voltage is, up there I wrote it I times 12. If you want a more compact version, you can just write the voltage is 12I. Let's see if it works. Use the equation, they say, to determine the voltage when the current is 6.2 amps. Okay, well, voltage is 12 times, and our current is 6.2. 12 times 6.2 is 74.4, I believe. And now, I was going to say we could check this against our graph, and quite often you can. Unfortunately, we can't do it here because they're asking about 6.2 amps, and our graph only goes up to 4. If only we'd had more graph paper, and we could track this line a little further, we could follow it all the way out to 6.2 amps, see what the voltage is the same way we did in question C, and see if that 74.4 is correct. But since we don't have a big enough graph, we just have to trust our formula this time. Finally, the resistance is calculated from V equals IR. This is a famous electronics formula called Ohm's law. State the resistance in this circuit. Well, we were saying that our voltage is the current times 12, and they're saying that corresponds to V equals I times R. These are obviously related. These are obviously related, and so it looks like in our circuit these last two are related, which would mean the resistance is 12 ohms.